This is part 3 of our series on the structures and properties of matter. And on this video, we're going to be focusing on the way that energy and pressure affect the motion of particles within a substance. And we define that through the states of matter called solid, liquid, gas, plasma. These are the ones you may have heard of. And of course, there are other states of matter actually, but these are the ones you will see in everyday life in the world. And that's the ones we're going to be talking about. But the states of matter are things that we use to describe a certain behavior of matter when it has a certain amount of energy in it or is under a certain amount of pressure. But before I get into that, I do realize that at no point in this lecture series I actually define what matter is. And that's because it's not so easy. You will hear that middle school definition that says it's the stuff that takes up space and has mass, but that's actually not accurate. Matter is the stuff that makes up the universe. And there are examples of matter that don't have mass and that don't take up space, like photons, which are particles of light. They don't really have mass or take up any space, and so per se. And so it's a little more complicated than that. But in general, for middle school terminology, you can use the whole, it's the stuff that takes up space and has mass. But a better definition would be the stuff that makes up the universe, which is interchangeable with energy, right? That whole EMC square thing, that matter and energy are interchangeable with each other. So back to middle school world here, what is happening to matter depends on the amount of energy that it has, or that it holds. Now, we're talking about heat energy here, and we're talking about thermal energy. What is that? So thermal energy is something that you can have, right? So it's how much particles are moving around and how much the size of the particles, all of that affects the amount of thermal energy a substance or system has. But when the energy is being transferred from one particle to another or from one system to another, we call that heat. So heat is the name for thermal energy in the act of being transferred. So you cannot have heat, you can transfer heat, right? So it's energy as it's being transferred. And there are a lot of different ways to transfer this energy. There's conduction, radiation, convection. We learned about that in the Earth Systems and Materials Content Assessment. Conduction, again, is the one that when you touch it, like you touch a hot stove, or when the core of the Earth touches the mantle and heats it up, that is conduction. Convection is when something that is hot or has heat, you cannot have heat, has thermal energy, moves and carries the energy with it. And an example of that would be convection, with hot air rising or with mantle plumes, right, that carry the heat from the bottom of the mantle to the top of the mantle and then end up touching the crust by conduction again and making the crust become hotter. So these are examples of those energy transfers. And then there's radiation, which is when energy is transferred through light waves, specifically infrared radiation, which is considered heat. The sun warms up the Earth that way. The Earth loses energy to space that way. And those are examples of heat transfers. So like if you stay far away from the stove, you're going to be heated up by conduction. As you approach it, the hot air coming from it will hit you. And that hot air moving is convection. But when you actually get hit by the hot air and the particles hit you and transfer the heat to you, or when you touch the stove, that's conduction. Now, heat isn't the same thing as temperature, but it does affect temperature because when you absorb heat, the particles will tend to move more. And as they move more, they will actually connect to each other less as well and start becoming more chaotic. The measurement of the amount of kinetic energy that the particles have or how fast they're moving is what we call temperature. So it's the average kinetic energy of the particles within the system is what we measure as temperature. There could be particles which are not moving as much, but as overall, the system or the substance, the more it moves, the higher the temperature. And that's going to be true. If it's absorbing heat, it's going to gain temperature because the particles are end up moving more. So that, of course, affects the states of matter. You may have heard about them: solid, liquid, gas, and then plasma. As you go in that order, you are gaining energy. You are gaining temperature. You're getting hotter and hotter. The states of matter are just descriptions of how the substance overall is acting or how the particles are acting on average. You could have particles in a solid, which are moving very fast, and particles in a gas, which are not moving very much at all. But on average, most of the particles will be moving in a certain way. In a solid, they're kind of locked in place. In a crystal, so if you hear the word crystal, that's going to be forming when things freeze, when they form into a solid. A liquid is going to be less connected. the particles are still have somewhat attracted to each other, but they're allowed to flow past each other. While in a solid, they can mostly vibrate in place. On a gas, there's so much energy that they're moving so chaotically and so fast that they barely interact with each other and they're flying around. In a plasma, that is taken to an extreme where the actual electrons around the atoms are actually dispersed chaotically, moving around the cloud of gas, and the gas becomes what it's called ionized, which is what plasma is. So in Earth, you can see that a lot. You can see clouds made of water vapor. You can see lakes and rivers made of liquid water, and glaciers made of ice. And that's actually what's special about the Earth, is just close enough from the sun or far enough from the sun, just right, that all three states of matter can be seen in water. And that is what allows the ecosystems of the Earth to be so diverse and perhaps life on Earth to be possible the way it is. Solid is certainly easy to find on the Earth. A lot of things on the Earth are solid. You have the atmosphere of the Earth, which is gaseous, right? Hydrosphere, which is liquid. Plasma, not so easy to find, but you do find with human technology in, for example, neon lights, right? It's something that you would find it's plasma. But the sun is full plasma. That's what it is. It is not burning. It's just really, really hot gas that's become ionized. Then there's, of course, the state changes and what they're called. Going from solid to liquid, it's called melting. Going from liquid to gas is called boiling, not evaporation. Evaporating is when you have a puddle, and then little by little, one particle at a time, they evaporate and become gas. And eventually, over long periods of time, the puddle disappears. But that's because each particle is absorbing energy and becoming a gas. When the entire liquid is changing state at once, you call that boiling, not evaporating. Then there's ionizing, when a gas becomes so full of energy that the electrons kind of rip off from the atoms and move chaotically around in a cloud of gas. That's called ionizing. Going backwards, deionization to bring it back to gas. Condensation, from going from gas to liquid, happens in clouds, happens when there's like dew in the morning. And you have, of course, freezing, when the solid comes from the liquid. Now, as you go to the right here, the arrows are blue because what that's representing is the fact that the environment is getting colder because the object is getting hotter. And that is increasing the amount of spread between the particles and decreasing the amount of interactions between them. Going left over here, you're going to have more interaction, less spread out, less motion, and the environment warms up, which is why the arrows are red, because you're giving out energy to the environment when you're freezing, when you're doing condensation, when you're deionizing. All right? Temperature tends to increase towards the right. Energy in the material tends to increase towards the right. We're going to see this again in another graph that I talk about later in this video. There are two more states of matter that are less common, but are also important. And state changes. Sorry, not states of matter. There are, by the way, other states of matter, like the Einstein-Bose state, which are very fun and particular to talk about in quantum mechanics, and other states of matter that happen in particular situations. But we're not really going to get into those because we don't see them very often. But these state changes, you do see them. When solid comes straight to gas, that's called sublimation. And you can see that if you put a piece of dry ice here on a table, it will just evaporate. It looks like it's evaporating, right? It's really boiling. Not really. All those words are wrong. From now on, you're going to use sublimation. Sublimation is when the solid becomes gas. And sometimes when the sun hits the snow in the morning, you can actually see the snow becoming gas straight away. Likewise, you can go from gas straight into a solid, and we call that deposition. And you can see that when frost happens in the morning, the water vapor gathers around the plants. It's very, very cold, the surface, and it will freeze right there, straight from gas. That's called deposition. Now, that word is also used in the context of, erosion and the minerals being deposited by rivers or by the wind into a different place, and then those deposits compacting and cementing to form new rock. That's the same word in a different context. We're not talking about that. We're talking about the gas becoming a solid. That's also called deposition. So one more way to think about the states of matter is their ability to hold their volume and their shape. Now, remember, volume is the space that the substance takes up. So a solid will hold its volume and its shape. It's what is called a crystal, right? It has connection between the molecules, and so it'll be so strong connectedly that will actually stay the same shape and the same volume. While a liquid will hold its volume, but it will not hold its shape. It takes the shape of the container that it's inside of, right? So if you move the container around, it will move to take the shape of that container as it's changing position, right? So it does, however, hold its volume. It doesn't. It's not like it's expanding or contracting randomly, right? It does hold its overall size, but gases do not hold its shape, and neither do liquids, right? Meanwhile, gases don't even hold a volume. They just spread out and take the space that they can take up, right? So if there's a room or a container, they will take all of it. They will spread out evenly throughout it. And that, again, has to do with the amount of connection that there exists between the molecules and the amount of thermal energy and how much motion the molecules have. Solids can stay in their shape because they don't have a lot of energy, and they're just kind of vibrating in place, locked into a crystal. Liquids, as they move past each other, they can hold its shape because it's somewhat of an attraction, but not, its volume because it's somewhat of an attraction, but not its shape because there's not enough attraction to hold its shape. They move, they flow, right? The gas both flows and spreads because there's no connection at all between the molecules. Now, what about physical changes or chemical changes? When you're talking about state changes, which one is it? Well, you have to ask yourself, is it still water when water evaporates or boils? Is it still water as it freezes? Yes, it's still the same chemical. You didn't change the substance, and so it's going to be a physical change, right? Water is still water when it freezes or boils. It's just in a different state. This graph shows something interesting that we haven't talked about yet as we talked about state changes, which is the idea that as temperature increases and energy increases, yes, you are changing the states. But something interesting happens to the temperature during the state changes. So look at here in freezing and melting, right? Do you see how the temperature is not changing even though the heat is being absorbed? So the heat energy is increasing, and yet it's staying in the same temperature. That's because all of the energy goes into breaking the connection between the bonds in the ice, making it melt into a liquid. Only until all the liquid actually happens, until the ice is gone, then it will stop picking up energy again and warming up as it becomes a liquid. So that's interesting that ice melts at exactly 0 degrees Celsius if you were at atmospheric of sea level, right? Pressure of the atmosphere at the sea level. And we're going to talk about that in a second, but that pressure also matters. But if we're at sea level exactly at 0 degrees, that change will happen. But until all the ice is gone, it will stay at 0. And all the energy is going to break into the connections between the molecules. And then after the connections are broken, the molecules will start to move more, and it will warm up as it is becoming a liquid. Then it hits that plateau again as it starts to boil. Until all the liquid is gone and all the connections are broken, it stays at 100 degrees Celsius at atmospheric pressure of a sea level, right? And it stays at that, and only until everything is a gas, then the gas can warm up and becomes hotter than that. Notice also that condensation and freezing also happens in those same temperatures. So condensation and boiling will both happen at 100 degrees, right? So the gas will stay at 100 degrees if it's doing condensation as well. But then when is so is it condensation or is it boiling that it happens at 100? Well, it's both. It depends. If you're adding heat to the substance, it's going to end up boiling. But if you're removing heat and the environment is getting warmer, then it's going to cause condensation. Which means, by the way, every time condensation happens, technically that warms up the environment around it. And likewise, every time boiling happens, it cools the environment around it. And that's why we have sweat in our skin, because as the sweat evaporates, that actually technically cools our skin because the environment gets colder as the object gets warmer, right? So the water takes the heat with it to become a gas. Likewise, with freezing and melting, it's exactly at 0. So if you take the heat away, it's going to freeze. But if you give heat to it, it's going to melt, right? If the environment gets hotter, that means it froze. So every time ice forms, the environment around it actually warms up. So in a lake surface, when the ice forms, it's actually warming up the surface around it. So that actually helps the environment when icing forms. Meanwhile, when it melts, then it actually must absorb the heat from the environment. But the temperature stays the same during those state changes until the entire thing changes, entire substance changes state. So if you had a thermometer on a glass with ice, it will stay at 0 after it gets to 0, and it will stay there until all the ice is gone and melts, and then it will start going and picking up energy. And the same thing happens when it's boiling. It will stay at 100 flat. It will not warm up more than that until all the gas is gone. All right, there's a couple more things we still have to talk about, but before we do that, let me review one more time that as you add heat to a system, the particles move faster and lose connection. And as heat is removed, they move slower and connect more. That means as you move from solid to gas, the amount of interaction between molecules decreases, and the amount of kinetic energy between the molecules actually going to end up increasing. But we did mention that pressure also matters, and we haven't talked much about that yet. What does pressure have to do with the state changes? Well, you can change actually the state of matter without changing temperature by changing the pressure. What is that about? If you actually compress gas, it turns into a liquid. I don't know if you ever played with a compressed gas can they use to spray and clean up stuff. That usually, you sometimes see liquid coming out of that. Well, that's because inside of that compressed gas, it's actually a liquid. You know, propane tanks in the back of people's houses, when they have propane tanks, a lot of it is actually in liquid state because it's compressed. But as the gas expands, it's allowed to return into a gas format. So the pressure of a gas keeps it into a liquid form. Likewise, if you compress a liquid enough, it actually turns into a solid. The Earth's core is solid, even though it's super, super hot. That's because of the immense amount of pressure that the layers of rock above it are doing it to squeeze it. So even though it's hot, it cannot melt. It stays as a solid. The opposite is true. If you take away pressure, things change state too. If you have a glass of water and you take it to outer space, it will boil, even though it's not being heated. And that's because there's nothing holding those molecules together into a liquid, and it will just evaporate. So that means that pressure also matters to determine the states of matter, right? So what is pressure though? Pressure is really just particles hitting and colliding with the surfaces around them. So what does that have to do with temperature? As you increase temperature, and if the container is sealed at a certain size, like you see the pictures over here, if the size does not change as the temperature increases, if you warm it up, the particles will start to move around more chaotically and faster, which means they will collide more with the surfaces of the container, causing an increase in pressure as well. So usually with an increase in temperature, if the container stays the same size, you will also see an increase in pressure. But in the atmosphere, something interesting happens. As you go higher and higher in the atmosphere of the Earth, there's actually less air. All right. So the air is squeezed by the weight of the air above it and by the gravity pulling it down. So as you go higher into the atmosphere, the air gets thinner and thinner because of the opposite of that. And as the air gets thinner, though, there's less particles to collide, which means there's less pressure. But how does that affect the boiling point and the melting point? Well, because there's less pressure holding the liquid down or holding the solid down, it means it becomes easier for things to boil and easier for things to melt, right? So that means that it changes the boiling point down because it makes it easier to melt. So it don't need to be as hot for it to boil. And it changes the freezing point also because it's easier for things to melt. So it doesn't need to be as cold for things to freeze, or hotter, it can already melt. So it will actually change those freezing and boiling points. All right. So that affects cooking though, because if you're living on top of a mountain, for example, when you try to cook, and water will start boiling at a lower temperature, maybe 96, maybe 94 degrees. And that means that it doesn't cook as hot, and it takes longer for the food to actually cook because it cooks at a lower temperature. But you can make up for that by using a pressure cooker. So the way the pressure cookers work is that the steam and the heat gets trapped inside of that pressure cooker. And as more and more steam evaporates, the pressure inside of it increases more and more, preventing more steam from actually happening. As the pressure increases, it squeezes the liquid in place, preventing it from actually evaporating. Meaning, instead of water boiling at a 212 normal boiling point in Fahrenheit, it will boil at 250 or 260. So in Celsius, instead of boiling at 100, it might boil at higher than that, 150 or even more, depending on how strong the pressure cooker is. That means that the food can cook at a higher temperature, which means it will cook faster, because both the pressure and the temperature are higher inside. And that, my friends, is the overview of this third objective of structures and properties of matter. I hope you found this lecture series useful and that it helps you pass the exams. And don't do anything that would make you more proud. I'll see you in the next one.